The Milky Way is a tremendous structure in space containing billions of stars and trillions of planets. In their turn, these objects are surrounded by gigantic clouds of interstellar dust and scorching hot gas streams. All these components make up the bizarre and fascinating picture called galaxy. And today, we invite you on an exciting journey across it. % of the Earth's total mass. In this case, provided a space object's orbit lies far from the host star, this object is going to be either an ice giant or a cold super-Earth. Radioactive decay taking place inside the core will help melt some portion of the ice, which in its turn will help form a subsurface ocean, but the planet's outer layers will still remain frozen. If the planet happens to find itself in its star's habitable zone, its outer layers will melt and spill all over the surface in a boundless ocean. Theoretical calculations show that a planet with a mass 6 to 8 times that of the Earth may have a layer of water over 100 kilometers thick. The pressure exerted by this amount of water may reach 20,000 atmospheres, depending on temperature, impurities and other parameters. This is enough for some special exotic varieties of ice to form, like ones remaining solid even at high temperatures. In addition, unlike the familiar water ice, these modifications would be heavier than liquid water. For example, the density of ice 7, which is likely to form in these conditions, should be around 1,650 kilos per cubic meter. This ice settles on the planet's ocean's bottom and forms a massive cryosphere that envelops the more massive core. The opportunity to put these theoretical assumptions to test arose when a tiny and dim star was spotted 42 light-years away from the Earth. It was dubbed Gliese 1214. The diameter of this red dwarf turned out to be 5 times smaller than that of the Sun, with its mass just 15.7% that of the Sun. At the same time, Gliese 1214 is 300 times dimmer than our parent star, while its surface temperature is only 3000 Kelvin, or 2700 degrees Celsius. There is nothing particularly remarkable about the star itself. To be blunt, it is just another nondescript red dwarf that looks like any of the billions of other stars in our galaxy. However, in 2009, a solitary planet was detected in its environs, which was dubbed Gliese 1214b. With its diameter measuring 2.5 times that of the Earth, this exoplanet is just 6.5 times heavier than our home planet. Straightforward calculations show the freefall acceleration on the exoplanet's surface to be just 91% that of the Earth. The average density of Gliese 1214b is approximately 1,870 kilos per cubic meter. Judging by this comparatively small value, the exoplanet cannot realistically be made up of mostly metals and rocks, as is the case with our Earth, for example. But incidentally, this average density value seems to confirm the assumption that the astronomical body is 75% water or water ice and just 25% rocks. Thus, it appears safe to suggest that this exoplanet is an ocean planet. The object lies very close to its host star. The average distance between them measures just around 2 million kilometers, or 0.014 astronomical units, which is 75 times smaller than that between the Earth and the Sun. Also, the orbit eccentricity is rather high at 0.27, slightly more than that of Pluto. This means that in its perihelion, Gliese 1214b is approximately twice as close to its star than when in its aphelion. As for its orbital period, it takes the planet about 36 hours to complete it. The red dwarf Gliese 1214 may be 300 times dimmer than the Sun, but this incredible proximity to the star makes the climate on Gliese 1214b scorching hot. Supposing the reflection coefficient of the surface of Gliese 1214b is the same as that of Venus, the planet's surface temperature is supposed to be around 393 Kelvin or 120 degrees Celsius. If, on the other hand, the surface is darker, the temperature may reach as much as 553 Kelvin or 280 degrees Celsius. Due to the fact that the orbit of Gliese 1214b crosses the star's disk, scientists are able to carry out spectroscopic investigations of its atmosphere. Still, the results are rather ambiguous. If this space object really is an ocean planet, its atmosphere is supposed to predominantly consist of water vapor with some accompanying gases. Interestingly, no lines of hydrogen, helium, or complex substances like water, CO2, and ammonia have so far been detected in the planet's spectrum. It is thought that the outer layer of the dense atmosphere conceals its true content from the observer. The conditions on the surface of Gliese 1214b remind one of what it is like inside a giant steam boiler. Interestingly, the atmospheric pressure in its lower strata should be at least 15 times as high as that of the Earth. As the ocean and the atmosphere are in a state of thermodynamic equilibrium, the border between them is rather blurred. No wonder, as the density of water vapor just above the ocean's surface is practically equal to that of constantly boiling water. As we look deeper at the lower strata of the ocean, the pressure will continue to increase until we reach the depth of 100 kilometers. With the pressure value at this depth, water will be unable to remain in its liquid state even at temperatures this high, and so we will see the bottom made up of dense and heavy ice, whose thickness is estimated to be upwards of 5,000 kilometers. Thus, most water on the planet is concentrated here. Below the cryosphere, there should be the core, made up of rocks and metals. Unfortunately, chances of life evolving on any ocean planet are rather thin, even if the surface temperature happens to be more favorable than on this one. This is so due to the fact that oceans on planets like that are too poor in terms of microelements that are vital for living creatures. Even taking into account meteorites that occasionally bombard the surfaces of these celestial bodies, the chemical diversity is simply not good enough for life to originate here. Still, studying ocean planets poses a great scientific interest. According to NASA's mathematical modeling estimates published in 2020, there may be billions of planets of this type in our galaxy, both cold, harboring an ocean under an ice shell, and warm, like Gliese 1214b. Water is one of the most widespread complex chemical compounds in the universe, and this means that the chances of discovering new ocean planets are quite optimistic. "650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass isn't sufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, and amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around a billionth of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. Earlier, in one of our previous videos, we have already taken a look at some terrifying and lethally dangerous worlds discovered in the vast expanses of space. With some of them extremely hot, others are located close to insanely powerful sources of radiation, and yet other ones are peculiar for some bizarre features on their surfaces. However, we haven't quite exhausted our list of the most horrifying planets, and now it's time to see some more. Our first stop is 202 light-years away from the Earth, destination K2-141, an orange dwarf. Its mass is roughly 0.7 that of the Sun, and its radius measures 68% that of our host star. With these parameters almost perfectly proportional, the star's temperature reaches 4,600 Kelvin, which is about 20% less than that of the Sun. And now to the planet in question. Just 0.007 astronomical units away from its star, there lies a really bizarre world, designation K2-141b. This rocky exoplanet is 5 times as massive as the Earth, with its radius 1.5 times as big as that of our Earth. All this gives us grounds to assume that the gravity on the planet's surface is at least twice as strong as that on our planet. The heavy metallic core, meanwhile, accounts for 20 to 50% of the planet's overall mass. It takes the celestial body about 6.5 hours to complete a full orbit around its parent star. Being extremely close, it is tidally locked to it. That is, it faces the star with one and the same side at all times. Observations show that the temperature on the planet's day side reaches 3270 Kelvin or 3000 degrees Celsius. This is enough not only to melt most rocks and metals, but also to effectively evaporate them. The day side of the planet is assumed to be covered with a lava ocean that never ceases to boil. The atmosphere is thought to be rather exotic, made up of steams of heavy metals and silicates. By contrast, the planet's night side is incredibly freezing. According to estimates, the temperature of most of its area is tens of times lower than that on the day side, and on balance, its values are supposed. And whenever some of them are solved, they add to our knowledge about the universe around us. Are we to solve all its mysteries someday? Time will show.